I'm Melissa. I'm Asmi.
I'm Anika.
I'm Shannon.
I'm Audrey.
I'm Daisy.
And I'm Waya.
And we're the Computer Vision Group, and we're mapping global poverty with computer vision. Recently, the United Nations published a list of sustainable development goals in order to ensure a better future for generations of the future to live in. Out of the 13 goals listed, the top most priority was to end global poverty. In fact, the problem of global poverty extends far beyond a scope you can fathom. According to UNICEF, 22,000 children die each day due to poverty. 783 million people live below the international poverty line of around $2 US. We have the resources, but we don't know where to distribute them due to the lack of data. Today, we produce enough food to feed 10 billion people, which is the estimated world population of 2050. The existing data collection methods are insufficient, and they're limited to door-to-door surveys. So as you can see, like the white spaces is where there's like no data on that area. And this is a map of Uganda, which is where we get our data from. Door-to-door surveys are too expensive. They're time-consuming, which makes it hard to update data. And some countries keep their data confidential due to political reasons, or they can't even like afford to have these surveys. So our approach is to use computer vision on satellite images to determine what areas are in poverty, so people know where to distribute the resources that we have. For our project this week, the past week, we looked specifically at satellite images of Uganda, and our goal is to do, or what we did was do binary classification on satellite images, and we determined whether or not that area was impoverished or not impoverished.
So, just reiterating what Tony said, we use satellite images from Google Maps, and then based on the landscape patterns such as infrastructures or roads, we're able to determine whether or not our image represents an area of poverty. And so to actually train our machine learning model, we have to use pre-existing human annotated class labels. This helps our data find a general trend between this predefined data in order to predict an outcome for new data it's never seen before. So our data set consists of 641 images that look like this, and we separate all of these images into 3 sets: train, validation, and test sets. So we use our training data to find similarities between our images, and then we use our validation set to tweak our hyperparameters in our model. And then lastly, we use our test set to test our model on data it's never seen before.
Like Alyssa mentioned, we will be using pre-labeled data of regions that are above and below the poverty line so that we can predict labels in future image data. The approach of using computer vision and machine learning to sort new satellite images into 2 distinct groups, which are areas in poverty and areas that aren't, is called binary classification. Now we'll discuss the general pipeline that all of our models follow. After splitting the data into 3 sets, train, validation, and test, we extract the valuable features of these images. Then we pass the features to the fully connected nets for final classification, to which the input is a flattened image. The comms net extracts meaningful semantic features by using a local sliding convolutional filter. Finally, we output the probability that will determine if the image represents an area of poverty.
We tried several models of binary classification, such as logistic regression, as well as a fully connected neural network. So first, let's start off with logistic regression. So logistic regression uses a linear model to the data in order to estimate the probability of an event's occurrence. But there are several negatives to this model. For example, they can only draw linear decision boundaries. So as you can see in the diagram to the left, this linear model is not able to accurately represent the data. While on the diagram to the right, we can see that this non-linear model, which has more variance, is more accurately able to represent the data. Another negative of this approach is that it can only fit one template per class, meaning these templates are created by overlaying several images on top of each other. But as a result of this, it can't adapt to shifts in any direction and changes in orientation or color in the images. So if we take a closer look at the horse template, we can see that some of the images, the horse is facing towards the left, and in some of the other images, the horse is facing towards the right. And as a result, it makes it look like horses have two heads, which we all know is not true. Which is why we moved on to fully connected neural networks. So in here, we can see that all the neurons are connected to all the other neurons in previous and future layers. And we took the input as flattened images. And as a result, because we took images as flattened, we lost a lot of spatial information, preventing the network from capturing more meaningful patterns in the image data. For example, it lost meaningful patterns such as locally invariant features, which are basically meaningful patterns in the image that are staying consistent over across all images. For example, in a cat, a meaningful feature could have been their ears or their tail. So now, while we do have non-linear decision boundaries increasing the variance, we're not able to take advantage of these locally invariant features.
To analyze our data further, we utilize a convolutional neural network, and they're very effective for image classification. CNNs, like neural networks, are made up of neurons and layers with learnable weights and biases. Each neuron receives several inputs, calculates a weighted sum, passes it through an activation function, and finally returns an output.
There are many technical advantages to using a CNN. CNNs perform better than fully connected neural networks because they are able to learn invariant local features. These are useful because, for example, when we shift an image of a dog, the CNN will still be able to recognize the dog in the image. CNNs also contain multiple filters which can capture many different characteristics of the image data. Additionally, the network contains many layers which can gradually represent higher level semantic meanings of the image data. So now we know what a CNN is and the technical advantages of it, but how exactly does it work? First of all, the convolutional layer runs 3x3 filters throughout the entire image instance, and this is then passed to an activation function called radian. Then we pass the image data to a max pooling layer, which takes a maximum of 2x2 filters. And this is then, the main objective of these layers is to extract invariant local features. And the next step we do is flatten the image data. This is then passed into a fully connected neural network consisting of 3 layers, 2 of which contain 8 neurons, and the last which contains a single neuron. And that neuron classifies our data as impoverished or not impoverished using a sigmoid activation function.
So now we're going to talk about our actual experimental results. We chose to first train our data with a CNN because of the many advantages that we talked about earlier. So on the left, you can see graphs of the accuracy and loss of our CNN, where the x-axis is the training time and the y-axis is the expected accuracy percentage or loss. And you can see how over time the accuracy goes up and loss goes down, which is what we want. And you can compare this to the logistic regression graphs, where logistic regression was a much less expressive model, so you couldn't get that same curve. Additionally, the logistic regression has a pretty big gap between the validation and training data, which means we overfit a little bit. So our CNN model resulted in an accuracy of 84%, which seemed pretty well, at least in comparison to the previous models we tried. However, the more we tried to make it a more expressive model or use various training techniques like regularization, our model would always stop at a certain accuracy of around 80%. This suggested that there might have not been a clear pattern in our data set. And another thing we soon realized was that our data was also very imbalanced, with 80% of our data points in class 0, which represents places in poverty, and 20% of our data in class 1, which represents data that are places that weren't in poverty.
Okay, so now that we have identified the problem, which of course is as a result of the data, we want to find a way to lessen the impact that the data imbalance has on the model. So, first of all, we decided to use class weights. So, class weights assign a higher weight to the training examples that have label 1 in our model. Essentially, the model would emphasize the training examples that have label 1 to hopefully make up for the data gap. However, the class weights did not perform as well as we wanted it to, so then we decided to try balancing the data.
So we decreased the number of training examples with label 0 through indexing and shuffling. However, the severe decrease in dataset size resulted in our model not being able to train and learn the proper features. So after our experiences with the CNN and dataset, we ended up discovering that having the right data is extremely important in machine learning models. Even a well set up model will eventually be biased in its predictions if it's not trained with the right data. So after the CNN model, we decided to try another approach to see if we could find a more optimal model to solve our problem. So we trained a fully connected neural network with pre-trained features that had already been passed through a more complex convolutional model. So in our first tries, we decided to first overfit our fully connected neural net to see whether or not if the model was working and if it was actually training and learning features. So after our model started to overfit, we decided to implement dropout. And what dropout is that it disperses the decision making across all the neurons in the different layers to ensure that eventually the model will learn all the different inputs and not just rely on a few inputs to make a few neurons to make the final decision. So what it does is that in some of the layers it will choose some of the neurons to be 0 and train on top. We also implemented early stopping, which is really helpful in detecting overfitting. And so what happens is that when it sees that the training accuracy is increasing, but the validation accuracy is plateauing or decreasing, it will eventually kind of backtrack and stop at the model's most accurate inputs.
So another experiment that we attempted was to visualize the pre-trained image features that Daisy discovered. However, these features are 4,096 dimensional vectors, which are way too high for us to visualize as we're limited to like a 3D visual space. So we use a dimensionality reduction technique called t-SNE, and it reduces these vectors to 2 dimensions while preserving the relative distance between the data points. So we can see here that while there's some apparent clustering of the 2 labels, yellow is impoverished and purple is not, they overlap, which indicates that the boundaries aren't very significant. So going back again to our results, we were able to figure out that a fully connected neural network was best able to overfit the data. However, the convolutional neural network that we trained from the raw images performed the best on the test set with an accuracy of around 84%. So in conclusion, although global poverty seems like a massive problem to try and tackle, and it seems like there's no end in sight, we believe that we can make significant progress to be able to reduce this, because we were able to identify that there was a lack of clear data that was leading to like unequal resource distribution, which we can see in this map here where there's so much data that's missing within this. We will be able to use satellite images as our data, which is what we did, and we utilized computer vision, or more specifically a deep convolutional neural network, in order to classify images as being an area of poverty or not. However, we believe that we can actually take steps to further increase our accuracy rate. One of them being, as Audrey mentioned, that our data set was kind of imbalanced between the pictures that we had that were of areas in poverty and not in poverty. So we can use something called image augmentation to balance this gap. What this means is, let's say for example, in our case this would be an image, a satellite image of an impoverished area. But in this case, let's take an example of like a bird. And we can see that we can do different things to this image that makes it completely new images in order to better train our network. So we can do rotations of an image, we can change color values, and we can add noise and make sure that some pixels are more granulated or less granulated and do other things. And we believe that this can help increase our accuracy. Another thing that we believe that we can do is we can make sure that our model is able to identify more nuanced metrics of poverty. So we can make sure that it's able to detect whether an area needs specific types of resources like shelter or water supply or other resources. We also believe that we can expand our data set worldwide and ensure that we can take images from across the world to determine whether there's poverty or not, and not just in Uganda, but worldwide. But before I end this presentation, I have many people to thank. First, I'd like to thank the directors of this program for giving us this opportunity to be able to explore AI, and for all the speakers who've spoken here for giving us the opportunities to learn about the applications of AI. I'd like to thank Juan Carlos also, and most importantly, however, I think maybe our research managers for helping us out with this. And although
the counselors.
Yes.
Our amazing counselors.
Yes. And although we might not have a physical present to give you guys, we have our infinite love.